Hello, 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 ladies and gentlemen, and welcome back to more of the 2007 Euclid Math Contest. So, we are up to question number 8. Let's have a look here. So, question 8 has two parts. Both of them are written. And what have we got here? 8A. In the 4x4 grid shown, 3 coins are randomly placed in different squares. Determine the probability that no 2 coins lie in the same row or column. Okay, so this question's kind of similar to, you may have heard of sort of the 8 queens, placing 8 queens on a chessboard so that none of them attack each other. This is sort of like placing rooks on a chessboard, because rooks, they attack in rows and columns. So this would be like placing 3 rooks on a 4x4 chessboard so that they can't attack. That's sort of the intuition behind their setup there. Now, as for the probability, so I think with the probability, we need to sort of do what we usually do. Find the number of ways we can place these coins or these rooks so that they don't attack, so the coins aren't in the same row and column, and then also divide that by the number of ways that we can just place 3 coins on a 4x4 grid, so that no coin is occupying the same space as another coin. Okay, so that's 2 things we've got to do to figure out the probability. Let's get to it. So, which one do we want to do first? So we have a 4x4 grid, and we're placing the coins. So, say I take my first coin. I can really pick any row and any column. So there's 4 choices for the rows and 4 choices for the columns to place it in. Once I've picked a row and a column, that coin gets to be there. Okay. Now my second coin, I want to place my second coin. I can pick a row for it to be in, but I can't pick the row that this coin's in. So I've got 3 rows to pick from. Similarly, I've got 3 columns to pick from. And that allows me to, say, place my second coin. So here I had 16 choices. Now I'm down to 9 choices. It's almost as though by placing our first coin, we cancel it out and we're sort of left with this shrunk 3x3 board. Well, now the second coin comes along and it's canceled out some spaces. So there's 4 choices left for where we place our third coin. Pick a row, and pick a column. There's 2 choices of row and column left. So that's 4 different possibilities. Now we'd want to multiply all these together, because they're independent, but placing our first coin here, our second coin here, and our third coin here is exactly the same, ultimately, as placing our first coin here, our second coin here, and our third coin here. So we've made a choice here to place our coins in order rather than just placing all 3 of them at once. And we have to account for that. We have to divide by the number of ways that you can label these as 1, 2, and 3. And there's, we could label it 1, 2, 3, or you do 1, 3, 2, 2, 1, 3. There's going to be 6 ways to do this. So the number of ways to place these coins is 16 times 9 times 4 divided by 6. 6, by the way, is also 3 factorial. Really, the number of ways to arrange the first k numbers is always k factorial. So 9 and 4 is 36, so divide that by 6. We're just left with 16 times 6, and that's 96. So there's 96 ways to place these 3 coins so that they are not, and so that no 2 occupy the same row or same column. So that's going to be the top number, the number of desired outcomes for our probability. Now we need the bottom number, the denominator, the total number of outcomes. So there's 3 coins to place. This is going to be easier. First coin has 16 places it can go. Second coin has 15 places it can go. Third coin has 14 places it can go. Okay. And Once again, the order doesn't matter. So yeah, we have 16 squares in our board. And we're just choosing 3 of these 16 and saying, okay, that's where the coins go. The coins aren't identifiable. So once again, we have this same sort of thing. Well, you place in the first coin, the second coin, and the third coin. But again, you have to divide by 3 times 2 times 1. Because otherwise, you're counting extra. So that's 16 times 15 times 14 divided by 6. The 15 has a factor of 3 in there. And the 16 has a factor of 2. So really, this is 8 times 5 times 14. Or 40 times 14. And that's 56 times 10, so 560. So our probability is the number of outcomes that we want divided by the total number of possible outcomes, so that's 560 there. And we can simplify that. So that's 16 times 6 over 8 times 5 times 14. Well, the 8 and the 16 and the 2 from there will cancel out. So it'll be 6 over 35, 5 times 7. Yeah. So there's our probability. 6 out of 35 times you'll get the coins so that they don't have so that no 2 are in the same row or same column. Alright. That's not so bad. Now, let's take a look here. There's a B part we still have to do. So B, in the diagram, the area of ABC is 1. Okay. Trapezoid DEFG is constructed so that G is to the left of F. DE is parallel to BC. And EF is parallel to AB. And DG is parallel to AC. Okay. Determine the maximum possible area of trapezoid DEFG. Interesting. So we know the area of ABC is 1. So it's definitely, at most, it's 1. But I have a feeling, because they've mentioned that G is to the left of F, we're gonna sort of be limited there. Alright, well, let's draw a bigger version of this picture and see what we can see. Alright, so we have a bunch of parallel lines. And because we have parallel lines, we're going to have just a whole bunch of similar triangles. Okay. That'll have to be check, and that'll have to be dot. Yeah, okay. Yeah. Alrighty then, so we've got some similar triangles. All of these red triangles are similar to our big triangle, ABC. I suppose I should label them. I think it was ABC this way. Nope. They went counterclockwise for some reason. That's okay. And it was D, E, F, G, right? Yeah. Okay. So there's our picture, and we've got a whole bunch of similar triangles. Now, the area of DEFG is really just the area of ABC minus ADE minus EFC minus BDG. Okay, just get rid of these red triangles, and you will get the area of this trapezoid. Okay. Now, ABC is similar to ADE, is similar to, I've got to make sure I get the order of these right. DBG, similar to EFC. Okay, that's clear from the angles that we've put on the diagram. Alright, so I'm going to let AC, I'm going to call that length B. I'm going to call AB C, and I'm going to call BC A. And I'm going to let P, Q, and R be the ratios. So we'll let how do I want to say this? So when you do when you have similar triangles, the lengths are in a common ratio. So I'm going to let AE, that's going to be similar to AC. I'm going to say that that's P times AC. And I'm going to say that BG is Q times BC. And I'm going to say EF is R times AB. That was probably a nicer way to write all that out. Yeah, FC will be Q times... Nope. I just wanted a slightly more elegant way to write this. So AD will be P times AB. BG will be Q times BC. And CE will be R times CA. So that's P times C, Q times A, and R times B. Alright. Now the nice thing about similar triangles, if you know the common ratio of the lengths, you know the common ratios of the areas. So triangle DBG has area of P squared. No, not P squared, Q squared. Alright? Well, so it's Q squared times the area of ABC, but we know ABC has an area of 1. And triangle EFC has area of R squared, and triangle ADE has area of P squared. Okay, well that gives me a nice expression for the area of DEFG. It's just 1 minus P squared minus Q squared minus R squared. So DEFG, 1 minus P squared minus Q squared minus R squared. Alright, now, is there anything else we can do? So we want to maximize this area. So to maximize area, we must minimize P, Q, and R. Well, no, technically we must minimize P squared plus Q squared plus R squared. Because this is really just 1 minus P squared plus Q squared plus R squared. I can't change the 1, but depending on what P, Q, and R are, I can change that sum that I'm taking away. And if I'm taking away something, I want to take away the smallest thing possible to make the biggest thing possible. Okay. So we need to minimize that. Fine. But we also have the condition we also want G to be on the right of F. Okay. Maybe the question couldn't be done. I mean, you would. I don't think you'd have a. Yeah, you wouldn't have a trapezoid there. Okay, so if G is to the right of F, if we take a look at our picture again. So this is, so it was P, Q, R. So this is Q times BC. This is R times BC here. So if G is to the right of F, then these guys have to be less than the total length of BC, and that tells me that Q and R has to add up to less than 1. Now, as soon as I have... Oh, I can do a bit more, because D and E are here. So, I know that AC is AE plus EC, but that's PAC plus RAC. So, dividing both sides by AC, we get 1 is P plus R. Similarly, the other side, this side over here, AB is AD plus DB, and that's PAD plus QBD. No, QAD. No, QAB. Yeah, both of these should be ABs. And dividing both sides by AB, we get 1 is P plus Q. But that tells me Q and R must be equal to one another. And they must also both be 1 minus P. Alright, so this is simplifying things. So Q plus R needs to be less than 1, so that means 1 minus P plus 1 minus P is less than 1. But that's 2 minus 2P is less than 1, or 1 is less than 2P, just rearranging things. So 1/2 has to be less than P. Okay, fine. And then we also have the area of DEFG is now 1 minus P squared plus 1 minus P squared plus 1 minus P squared. I can expand this out in terms of P, and then knowing this range of P values, I suppose we could minimize things. Maybe. We get 1 minus P squared. So the minus will apply to, so we'll get minus 1 plus 2P minus P squared minus another 1 plus 2P minus P squared. So we will get negative 3P squared plus 4P minus 1. So that's the area. Yeah. Okay. So this is a parabola, and now we want to maximize this value in the range that 1/2 is greater than P. Okay, but this is a downward-facing parabola, isn't it? In fact, can I do anything with this? Factor it in any way? So it's negative, it's going to have a P minus 1 and a 3P minus 1 as well. Okay, so roots are 1/3 and 1, so it's a downward facing parabola. Say 1/3 is here, we'll say 1 is there. One-third and 1/2 is about here. And the maximum, the vertex, is at 2/3, halfway between 1 and 1/3. So the vertex is always halfway between the roots. And since that's in the range that we're looking at for values of p, so, p equals 2/3. We'll maximize, and it would maximize it no matter what, I guess. I mean, this is always the maximum. It had really nothing to do with p being 1/2. Although if p had to be less than 1/2, we'd be looking at some value, really the value of p at 1/2, or the value of the area when p is 1/2. But, so p equals 2/3 will maximize the area. And what is that area? Well, we have a formula for it. It's minus p minus 1, 3p minus 1. So that's going to be minus 2/3 minus 1, 3 2/3 minus 1. So that'll be minus negative 1/3, 2 minus 1, so that'll be 1. So that'll be 1/3 in total. Okay, and what exactly did we want? We just wanted the maximum area. Determine the maximum possible area, 1/3. Maximum possible area of DEFG is 1/3. And that's going to happen if P is 2/3, then both Q and R are 1/3. So they hit 1/3 on either side. So this is 1/3 of BC, and this is 1/3 of BC, and this is 1/3 of BC. And this is going to be 2/3 of BC. And the height of this top triangle is going to be 2/3 of the total height. So what's left? 1/3 of the total height. So what's the area of this trapezoid? We're just double checking. With both of these being 1/3, by the way, we have guaranteed that G is on the left of F. Yeah, G is to the left of F. But it's going to be a height of 1/3 times the total altitude, and then 1/3 plus 2/3 of BC is just going to be BC. And so the altitude times BC gives us, and it should be a half. So this is going to be 1/3 of a half the altitude times BC, but we know that this is just the area of ABC. So it's going to be 1/3 times 1, and yeah, we're right. It is 1/3. Nice. So that finishes off question 8. We've done both the A and the B parts. Up next will be question number 9. I can't wait for that. I will see you guys there.